So what we talked about various chemical agents, ethanol, hydrogen peroxide, heavy metals, the halogens, all kinds of stuff. The last thing that I want to discuss with you is alkylating agents. For those of you chemical aficionados, and I know that pretty much everybody loves chemistry, right? Alkylating agents are the ones that can add an organic residue called the alkyl group to the molecules of proteins and nucleic acids. What is alkyl group? One of the examples could be something like this, okay? Or any type of long, not very long, but hydrocarbon chain adding to the protein or to nucleic acid. So if you add it to the nucleic acid, like here, okay, what's going to happen is nucleic acid is going to change its structure. And if it changes its structure, what else is changed? Function. Structure, it should be like a reflex by now. Structure, function, structure, function. You change the structure, change the function. You change the structure of the DNA, it means next round of replication you get mutations. Does that make sense? You get mutations, they may be deadly. Many rounds, cell will die. Or you modify proteins. You alkylate proteins. You alkylate proteins inside the cell, they lose the function, don't work as enzymes. Or you start to, this is called cross-link elements of the envelope, like the proteins in the outer membrane of gram-negatives, or the carbohydrates in the outer membrane of, sorry, not the outer membrane, the cell wall of gram-positives. It will change the rigidity, the conformation of those molecules, altering the structural integrity of the envelope. It can make cell more permeable or something like that. Does that make sense? So all those agents are very effective, it turns out. Among those, formaldehyde, which is gas, it's water solution that we know as formalin, and glutaraldehyde, which is liquid. Formalin is used, as you know, to preserve corpses for medical purposes, or any other biological specimen from decaying. It both inactivates microbes that can be potentially in the biological specimen, and formalin will also inactivate intrinsic proteins, enzymes that belong to the specimen, so those enzymes will not contribute to the rotting process, decaying process, right? Formaldehyde is the gas, so toxic gas, gas that has higher irritation potential. It is used to sterilize rooms. Remember we watched this little fragment about BSL-3, BSL-4 facilities? Well, imagine what will happen if you have some piece of equipment in that facility, a computer. You have a computer, and yes, there are computers in those facilities, and it breaks. So what are you going to do with a broken computer from that facility? Can you repair it? Especially if you need to take something out of the room. No, you can't. Or, well, computers, come on, at this time computers like less than $1,000, you can buy a new one, okay. What if you have more expensive piece of equipment, like a hood, by safety level hood, not this one, but by safety level hood can run like 15,000 bucks, okay, and something is broken and you have to take it out to repair. You can invite a repairman, but the problem is that repairman has to undergo a training. So you have to pay this poor fella for all the hours he or she will spend, getting ready for the task, just learning how to dress up and stuff. So you want to take something out of the room. The only time you can do it is after the decontamination procedure, which happens once a year. If you bring something there by accident, it'll stay there till next decon. During decon, they pump formaldehyde into the HVAC and it recirculates through all the rooms for several days, and then they unplug the supply, formaldehyde supply, and start to circulate normal air. And after a week or two, they let people in, and it stinks awfully because not all formaldehyde is gone. You work there, like clean up or order everything, tied up everything for 2 hours. You come back to the normal life. Your eyes burning, your nose is burning, your throat is burning, because still there's enough formaldehyde. Not enough formaldehyde to kill you, but enough formaldehyde to irritate the hell out of you. Okay, so formaldehyde is very strong irritant, but it's effective, it's sterilizing, as all other agents that we're going to mention. For instance, ethylene oxide and beta-propion lactone. Ethylene oxide is the gas that is used to sterilize medical equipment, the plasticware. The advantage of it is that first of all, it's very chemically active. So it has high sterilizing capacity. Another advantage, it doesn't stick around like formaldehyde for that long. Does that make sense? So you can essentially treat batches of plasticware with ethylene oxide, and then when you ethylene oxide will decompose in a fairly short period of time without any trace. Does that make sense? So there are no traces, you're not going to poison anyone. Okay? Is that clear? Now, we're moving on to this interesting table. We're going to talk about this table, and I will conclude this topic with what I expect you to know about the sterilization techniques. So this is the stuff that you may or may not have at home, right? And it's just interesting to look what we're dealing with. Lysol and Clorox. Clorox, contrary to its name, doesn't have any chlorine there. It's the quaternary ammonia. So when you see the label on the these Clorox disinfecting wipes, I think if I will pull it up on Google, you will see it says something like removes 99.9%, kills 99.9% bacteria. I would be very careful trusting this claim, because surfactants, first of all, they're not sterilizing, right? Second, when you wipe it off, you mechanically remove the bacteria, first of all. Quaternary ammonia will affect the bacterial membranes, but they aren't even close to sterilization. The best they can achieve is disinfection of the surface, if not sanitization. Does that make sense? So, and 99.9%, it's kind of a lousy killing capacity. Because if you have, I don't know, 10 million bacteria on the counter after you were cooking chicken, and you destroy 99.9%, then you have 10,000 cells left, which is plenty to spoil the food. Especially if it's salmonella, it's more than enough to give you salmonellosis. Right? So be careful with those marketing claims. Tilex. The mildew removers contain sodium hypochlorite, which when you spray it on the tiles, right, it starts to produce actually free chlorine. And that's why mildew gets all cleaned up almost by itself. Sometimes you don't even have to scrub if you leave it on for a while. That make sense? Well, the downside, what do you have when you spray, when you work with it? How does it smell? Offensive, yes. Chlorine, funky, offensive smell. You have to work in the well-ventilated rooms and stuff like that. Because, and you see, the more effective the chemical is, the more toxic it is for humans. That's one of the biggest take-home messages I want you to understand. You can't have mild effect on humans and huge effects on bacteria because all of them are living, right? We're living, bacteria are living. Triclosan in the hand soap. We had a discussion about this. First, it wasn't very effective in the first place, and microbes developed resistance. Another Lysol is another example of a detergent as the most active compound. So again, not extremely good. Contact lens contain chloric hexidine, which, as you remember, is a great thing actually. It has a good disinfecting capacity and very mild on human tissues. And it makes a lot of sense because if you put something, you don't want to put your contact lens in like Clorox, okay? It's going to clean them up well, but your eyes are not going to appreciate that. Another example, I don't really know this particular brand, some towels. Is that like a wipes? Yeah. So again, quaternary ammonia, another example of surfactant. You see, surfactant takes most of the common household cleaning agents because it's mild enough. It helps you to remove like soil, okay, dirt, and on the side, the good icing on the cake, it kills some bacteria. I'm going to skip another example of triclosan. Mouthwash and hand sanitizer contain ethanol. It makes perfect sense in both, It's fairly safe. If you swallow some of that mouthwash, you're not going to get killed. And it will destroy some of the microbes in the mouth. Not all of them, which is good, because you need to maintain some of the microbiota. The hand sanitizer, what I want you to be aware of, and that's quite serious. A lot of I carry hand sanitizer in the car. Because when we are on the road and we make a pit stop, we wash our hands, but I can't really trust my kids, so I give them hand sanitizer. But if you're dealing with bacteria, it will kill them. If you're dealing with the virus, like some caliciviruses or adenoviruses that can cause digestive disease, then this is no help, really. I think we discussed it regarding the cruise ships. Then on the cruise ships, they start to install hand sanitizers. That on cruise ships, to fight norovirus, they started to install hand sanitizers, which have absolutely no effect of norovirus whatsoever. I mean, it's good to get rid of bacteria, but one of the major causes of diarrhea outbreaks on cruise ships is still going to persist. Pine sol, phenol, okay, is a main active compound. Of course, there's a surfactant to remove the dirt, but phenol will have antibacterial. From the standpoint of the control, pine sol would be probably the most effective and the most toxic. Okay, and this, I don't really know. Sodium chloride, I don't know what they added for into those allergen eye drops. Seriously, I would say it's probably a preservative, because I don't see how sodium chloride can treat the allergy unless it burns it out together with your eyes. Now this is more for the reference, okay? The effects, the level of activity, how toxic it is, for sorry, for the methods that we discussed. Say, question? This is a great question. Is that worth using? You're the first person in 3 classes. Okay, so is that a good idea to use disinfectant spray in the house? Depends on what for. So what do you use it for? What are your hopes? Hmm? Okay. Okay. So what are you using it on? Go ahead. Let's put it this way. If you spray it on the car seats, if they are cloth, then if they are leather or faux leather or whatever, the smooth surface, and you wipe it, yes, it will help. Okay? But it mostly helps because you mechanically remove it. Does that make sense? Okay? Same goes for the steering wheel. Okay, you spray it, you wipe it. Again, depends on what type of disinfectant you're using. Hmm? Like you bleach it. That's probably the only solution to this, really. But if you go into the medical facilities and nursing facilities and then go back home, I would say that the one bacterium that you really should be concerned about is C. diff, because it forms spores. Others will die because of the desiccation. Couch is not a perfect breeding ground for microbes, honestly. Again, like in the kitchen, I always focus on the kitchen because if you cook, especially you cook poultry, which carries shitload of contaminants, and you essentially have a spoilage of the counter. If you want to prevent any cross-contamination, bleach it. If you don't want to bleach it, I sometimes, if I cooked chicken and it all got really messy and bloody all over the place, I will wipe it off with whatever thing I have just to remove all the crap. And then I pour some hydrogen peroxide, distribute it all over the place and leave it there. So it will evaporate. It will take care of most of the microbes. Because luckily, we are lucky that those microbes like Campylobacter jejuni and Salmonella and Listeria, they are pretty sensitive to cleaning agents. That makes sense? But the big take-home message, you see, the more effective methods are also more extreme. They either take the high pressure, high temperature, or more aggressive chemicals. That's one. What you have to know for the methods. If I ask you, what is the major mechanism for halogens? You tell me they oxidize things. That's all you have to know. Oxidative, okay? Are they sterilizing? Yes, in the high concentration. I ask you, is boiling sterilizing? No. Okay, what does it do? It denatures proteins. Does that make sense? So you have to know the basic mechanism, and you have to know the level of cleanliness that you can achieve with a certain method. That make sense? I'll post the study guide. I hope it will help. Any questions? Let's have some fun. So we get closer and closer to clinical things, clinically related, and we're going to talk about antibacterial drugs, and I stress it out, antibacterial, because I will include antifungal, antiprotozoan, antiviral in the chapters that we're going to cover a little later. So we talk about viruses, we talk about how to treat them. That make sense? Before we'll discuss the drugs that we have now. I always think it's a good idea to look back in history and see how it was before. The infectious nature of many diseases, as you remember, was known even in ancient times. People didn't know what causes them, but they knew that infection is contagious. We talked about usage of the copper shavings to treat or prevent wound infections in soldiers in ancient Greece. In fact, Chinese, which had civilization since I don't know when, were always looking for and searching for the potential medicines in plants and herbs. And I'd be honest, I'm rather skeptical about plants and herbs as medicine. However, I must say that not all of it is a snake oil. What I try to say is that there are plants that will help you with certain digestive problems, or I don't know, skin problems and whatnot, if they are prepared in a certain way. It's completely scientific. You essentially extract some active compound out of the plant. Does that make sense? The first effective drug against malaria, the quinine, was the chemical isolated from the bark of a tree. And that bark itself was the original treatment that South American aboriginals used to treat malaria. So all Westerners did, they isolated the actual chemical. Does that make sense? So another example that I love is artemisinin. We're lucky not to generally hear about that drug. That's the drug that treats malaria as well. The Chinese scientist who discovered artemisinin got the Nobel Prize in Physiology and Medicine about a couple of years ago, or 1 year ago, something like that. She literally went into the library and read ancient Chinese books on the herbal medicine. And by carefully combing for years through that literature, she identified the species that was effective, and she tried them and scientifically showed that this herb helps, and managed to isolate the active compound. Does that make sense? So it's worth a try. But you can appreciate that those attempts, that usage of those medicines, it wasn't scientifically based, purely scientifically based. It wasn't double-blinded, placebo-controlled, multi-centered study, right? It helped me, so it should help everybody else. So the first attempt to create the actual antibiotic was by Paul Ehrlich. 1909, his assistant, Japanese dude, whose name I blank on, of course, identified the drug that they called compound 600. Guess why 600? They tested 599 before that. That was able to kill Treponema pallidum, the causative agent of syphilis. So they were pretty happy about it, as I think people with syphilis. The only problem was that the compound contained arsenic, so it's pretty toxic. However, if you ask me, if I have a choice between the chronic syphilis and taking something with arsenic, I'll take arsenic 24/7. I'll show you maybe at some point pictures, or you can Google yourself, tertiary syphilis. Nothing pleasant to look at. Hmm? It's neurosyphilis. It's a tertiary, it's a late stage years after the initial infection. I would say that's lucky, because what else you can have? You can have cardiac syphilis or gummas, disfiguring lesions on the face and mucous membranes. It's really not a pleasant thing. Anyway, that was pretty much the first antimicrobial. Okay, that they tried. They pretty much did the high throughput screening. I also asked one class yesterday the question. I want to ask you the same question. Why do you think by the end of 19th, beginning of 20th century, the need in the effective antimicrobial drugs became so urgent? What is so important? Why it's specifically end of 19th, beginning of 20th century, and people started to actively search for antimicrobials? At this time, Lister proposed phenol for external treatment, but drugs were not available. What happened in the end of 19th? What was happening? It was like a continuous process. Yes, but don't think about diseases. Think about humanity. Huh? Sanitation improved, yes, but for some reason rates of infectious diseases started to move around. Steamboats, trains, industrial revolution. Look, people lived in the village. You have a village of 20 people, all of them die, who cares? That's it. There's no epidemic. You have, I don't know, a 15-story building with hundreds of families living in the same building. And they all get sick. Does that make sense? So this living in close quarters, establishing the travel routes between the cities, between the countries, allowed for quick spread of infection. So we started to appreciate the role of infectious disease at this time. Okay? That makes sense? Think about Spanish flu. 2 years and it spread all over the world. And it's 1918. So next step would be to, again, it's kind of confusing. So first, what is claimed to be the first synthetic antimicrobial? It's fully organic molecule, okay, called sulfanilamide. It was a dye synthesized in the research labs of BASF, the company, German company, by 3 scientists. And one of the first recipients, one of the first patients who received sulfanilamide was the daughter of that guy with the last name Domag. His daughter had a chronic streptococcal wound infection and was successfully treated by that dye. So, and it got marketed, and we still use drugs of that family right now. If you've heard about sulfamethoxazole, that belongs to the same family. Okay, but what we think was a turning point for antimicrobial therapy was the discovery of penicillin by Alexander Fleming in 1928. He returned back to his lab after the vacation and inspected some old plates with staphylococci. One of the plates had a fungal growth inside, and that fungus was surrounded by the clean area, so staphylococci sort of receded to the edge of the plates. Do you think he was the first scientist who saw that? He wasn't. But he was the first person to draw a conclusion out of it. He was the first person to think, well, if there is an area free of bacteria around that fungus, what is in this area? What does fungus do? What does it make? Not until the efforts by Florey and Chain allowed scientists to isolate the actual chemical that came from that fungus, Penicillium notatum. So the Quarry and Chain isolated penicillin, and they also developed the method for its mass production. Okay, so they started to grow fungus in large amounts and isolating the active compound, because before that, penicillin was probably more expensive than gold by weight. It was so hard to isolate it. Quarry, Chain, and Fleming all received Nobel Prize in Physiology and Medicine in 1945 for penicillin. As you may have heard, when people receive Nobel Prize, they deliver a speech. Stockholm, they dress in like funny costumes. Okay, and there's a king and queen, a lot of famous people, and yeah, and the person stands up and delivers the speech, the recipient of the prize. So Fleming delivered his speech, and a big portion of the speech was dedicated to one problem that was non-existent in 1945, but that problem that Fleming foresaw at the time. Problem linked to antibiotics. What do you think he was talking about? Resistance. Yes. It's amazing how he was able to predict. He was calling the scientific community to use antibiotics responsibly, because he warned that microbes will develop resistance, and in the 50s there were already a few resistant strains resistance to penicillin. It was absolutely right. Okay, so Dorothy Hodgkin in 46, she discovered, well, not discovered, established, figured out, revealed the structure of penicillin, which helped scientists to modify the structure, and by modifying structure, change the function, either altering the spectrum of the drug or tweaking its activity against the microbes, getting around the resistance, right? Now, and we were stuck with penicillin for quite a long time, and penicillin is mostly effective against gram-positives. Very few gram-negative microbes are actually sensitive to penicillin. So it was a big sigh of relief when in the 40s, Selman Waxman, I think he was at Rockefeller University, New York, but I may be wrong about this. He isolated the compounds that he called aminoglycosides, streptomycin, neomycin, and actinomycin, from the bacteria Actinobacteria and Streptomyces. You actually can buy neomycin in the pharmacy without a prescription as a component of antibacterial cream, topical treatment, right? And that was a great sign of relief, because that was the first broad spectrum antibiotic discovered. Another important thing is that Waxman suggested, now where should we look for antibiotics? In the soil. We should look in the dirt to find the new drugs. This history is not full. Not even close. I don't mention the discovery of tetracyclines, discovery of rifamycin, fluoroquinolones, the kind of latest hexazolidinones or diaryl quinolones. The reason for that, because once we realize the source, the soil, the environment, and we establish the procedures for high throughput screening, discovery of new antimicrobials became sort of routine. Unfortunately, this routine did not bring any breakthroughs in last years. That's downside. Okay, I'm not even coming close to discoveries of therapies for HIV which is a great breakthrough. If you think about it, in 1987, 88, when I was a kid, I heard about HIV. I was freaking out. I thought we're all gonna die. Seriously, I thought it's gonna be a plague, just a matter of time when I'm gonna contract it, which I hope is not. But I thought everybody's gonna die. Okay, it was so awful. Now it's a chronic disease. I mean, officially, WHO classifies HIV as a chronic disease along with diabetes and hypertension, which means with a proper management, people can live a normal lifespan. Magic Johnson. I'm going to be rotting in the soil, and he's going to be playing basketball. Now, general points of consideration for any drug that affects microbes. Source. Some drugs are natural, like penicillin. Some drugs are synthetic, like sulfanilamide. Some drugs are semi-synthetic. So you take penicillin, modify it, make, say, ampicillin or amoxicillin, it becomes semi-synthetic drug. You see the difference? Drugs can be cidal and static, bactericidal, bacteriostatic. In the healthy person, which one can we use? In otherwise healthy person. Immunocompetent, let's put it this way. Yeah, we can use cidal, we can use static. Static is fine. It will stop microbes from growing, and then immune system can kick in, right? If you have a patient whose immune system is compromised, you probably won't be able to get away with bacteriostatic drug. You need something that will kill microbes. Does that make sense? Now, some drugs show synergism, like trimethoprim and sulfamethoxazole. When they are combined, the brand name is Bactrim. So in each of them separately, trimethoprim and sulfamethoxazole, each drug is bacteriostatic. But when you put them together, the combination becomes bactericidal. Does that make sense? Right? So you put them together and they kill microbes. Spectrum. Broad versus narrow. Any thoughts? When you use what are the advantages, what are the disadvantages? When you use broad spectrum, when you use narrow spectrum, what's good, what's bad about them? Okay, broad can treat more. Yes, narrow. Probably so. Another thing, imagine that you have a patient comes in with a 106 fever, rash all over the body, bleeding out of his nose, seizures, diarrhea, and severe cough, and compromised lung function. What you gonna give him? Narrow spectrum or broad spectrum? Just broad, because you don't know what causes it, right? And then, if you can stabilize the patient, you wait for the cultures to come in. But if you know what it is, you can use narrow. What is the disadvantage of broad spectrum antibiotics? Not really, no. Yes, so first of all, they can more likely to induce resistance. Because the only true broad spectrum, well, there are several broad spectrum treatments that are equally effective against all microbes, like nuclear blast or burning, okay? Drugs usually have variable effectiveness. Although we say it's a broad spectrum, it's going to be, say, more effective against gram-negatives and slightly less effective against gram-positives. Does that make sense? Or vice versa. So it will successfully treat the infection and will induce resistance in other microbes without actually killing them. Does that make sense? This resistance is usually mediated by like enzymes and pumps, different kinds of resistance is a trait, let's put it this way, right? You agree with me? What defines a trait? Trait is the phenotype. What defines phenotype? Of what? Gene. So you have a gene that's responsible for resistance, or genes. You follow? What microbes do with the genes? Transfer them. So even though you may have a non-pathogenic bacteria carrying the resistance gene, this gene can be transferred to a pathogenic bacteria, rendering it resistant, and then you're going to be screwed. You see the problem number one? Problem number two, so-called superinfection. In famous C. diff, the broad-spectrum antimicrobials can really disturb the microbiome. Well, it can be, usually we talk about C. diff, digestive tract, but it can be a microbiome, the vaginal microbiome, and then women can have, for instance, fungal vaginosis. Okay, when normal bacteria go down and opportunistic pathogens kick in. So that's another problem with the broad spectrum microbes. And last but not least, the route of administration. So generally, we either take pills, or we take intramuscular injections, or we take IV. Make sense? I had somebody ask me why we don't do intranasal spray. Any ideas? Say again? This is number one. It's not going to be getting, well, what if you want to treat local? No, I mean like infection in the nose, like sinus. The problem, dosage, right? You think about the spray, it's just flu mist. The main problem with that vaccine against flu is the dosage. That's the biggest problem. Okay? Other than that, yeah, I agree with you. I mean, for sinus infection, it would be lovely to spray antibiotics in there. But how much can you deliver with each spray? And how much of it will be washed away by the mucus, and how much will actually reach the site? So IV, IM, oral. If you look at this graph, you will see that IV, which is red, has the highest levels of the antibiotic in the circulation that stay there for a long time. Intramuscular, green, and oral, blue, levels, the levels in the blood increase at a much slower pace, do not reach quite the same height, and stay there for pretty much the same amount of time. So IV seems like it's the best route. What are the disadvantages of the IV injection of the drug? Huh? Why it's bad? Why? So it reaches high levels. Why it can be a problem? That what every drug has, except for its good action. Yes. So if it has any toxicity, it will be more manifested. So you have to think whether you should give the drug IV or orally. Okay? So that's pretty much another big disadvantage, obviously, is the convenience. Because taking drug orally is easier for patient. If we talk about long-term antibiotic treatment, you're not going to stick the needle every time in the vein. You gotta have to insert a catheter. Does that make sense? And if you ever received a series of intramuscular antibiotic injections in the rear end, as the person who had this at the age of 10 for a week, I think it was 3 or 4 injections a day, you forget about sleeping on your back, okay? Because it hurts. So there are different considerations, but it turns out the main consideration for the route, the administration route, is the bioavailability of the drug, the ability of it to get, say you want to take a drug by mouth, but if it is not absorbed in the intestines, there's no point of doing that. You see the point? I can't remember from top of my head. Ampicillin and amoxicillin, they have different ability to be absorbed. I don't remember which one is which. One of them is IV. I think amoxicillin is or the oral, because it's easily absorbed. Ampicillin has to be injected. It's not absorbed in the intestines. You see? Now, if you want to treat systemic infection, like bacteremia, sepsis, stuff like that, you want to get it right into the blood, so it reaches the proper site. If you're treating something localized to the intestines, you need to think about something that will get into the intestines and will be active there. Does that make sense? So it's not only one factor of high concentration. You have to consider other things. Good? This is what they can do. So there are several targets. What are the components of the bacterial cell that are present in every cell? Plasma membrane, number one. Huh? Well, not nucleus, huh? Cytoplasm. We'll get to that. Huh? Well, not in bacteria. In bacterial. So what I mean bacterial cells. All bacterial cells have it. So cytoplasm, membrane, ribosomes, and DNA. 4. Okay? So you can see that we can target DNA, and all of them have to make RNA as well. We can target ribosomes. We can target plasma membrane. Targeting cytoplasm is really hard. I mean, it's easy, but if you desiccate a bacteria, you might as well desiccate a patient. A lot of microbes have cell wall, right? Do humans have cell wall in their cells? Well, thank you. Because unless you're made out of wood, then you do. But if you're normal, then you don't have cell wall. So cell wall targeting antibiotics will interfere with many microbes. And there are some critical metabolic pathways, like folic acid or mycolic acid synthesis, that we have drugs that interfere with them, right? So you see, there are not so many targets. Bacterial cells are very simple, okay? But we can target pretty much every element of the bacterial cell. And for this is the kind of a summary of the same stuff in the form of a table. And for the drugs that we're going to discuss, what I want you to know, basic mechanism, how they work. Basic mechanisms of resistance to them. We're going to discuss them much later, not today. And examples of those drugs. And first, I'm going to do the quick overview of what these guys can do. So first, we can inhibit the synthesis of the cell wall. When bacterial cell grows, it becomes bigger. It has to make new cell wall pretty much. If you inhibit this process and get rid of the cell wall, what's going to happen to the cell? It's going to pop. It's going to pop, right? The good way to figure out what something does is to get rid of it. like your thumb. You don't know how important thumbs are until you cut them off. Okay? Yeah, well, I've got two really nasty cuts on the thumb that pretty much I couldn't use it. It was awful. It was just, it was a nightmare. Yes, yes. And now it's better, but you get rid of something and then figure out what's going to happen. Okay, so we get rid of the cell wall, cell is going to pop. There are three different mechanisms that we're going to discuss. One mechanism is represented by different types of beta-lactams like penicillin. Another one is represented by vancomycin, and bacitracin is the example of the third one. We're going to talk about them in more details. You can inhibit the protein synthesis. If you inhibit protein synthesis, the cell is toast, right? There are two types of drugs, tetracyclines and aminoglycosides, that bind to the 30S subunit of the ribosome, bacterial ribosome, and screw things up. And lincosamides, macrolides, chloramphenicol, and oxazolidinones bind to the 50S subunit and screw things up there. By the way, speaking of the names, I know it doesn't sound very English. It's not me, I didn't invent them. Blame chemists. All those words like aminoglycosides or oxazolidinones were invented by chemists. You can disrupt the membrane. Okay, things like polymyxin B, which you can find in the topical antibacterial cream, are very effective in disrupting the membrane. Okay, there are some unintended consequences to that. You can inhibit nucleic acid synthesis, stop RNA from being made or DNA from being made, which also screws cells over big time. Or you can inhibit the metabolic pathways like folic acid synthesis. Without folic acid, cells cannot make nucleotides. Mycobacteria, like Mycobacteria tuberculosis, have to make mycolic acid as a component of the cell wall. The drug called isoniazid, isonicotinic, well, the brand name is isoniazid. We'll talk about it quickly. It inhibits synthesis of mycolic acid and is very effective for treating mycobacterial infections. And you will see that in many cases we'll have something like gram positives, gram negatives, gram positives, gram negatives, gram positives, gram negatives, and mycobacteria, because these guys, mycobacteria, are notoriously hard to treat, just awfully hard to treat. Okay. There's a new generation of drugs called diaryl quinolines. These guys inhibit ATP synthase. So cell stops making ATP. They're very effective. They targeted against mycobacteria. No surprise, they're also pretty toxic. Okay? Follow me so far? So again, we're going to talk about, it's not a pharmacology class. I'm not going to talk about each and every drug known to humanity. But I want you to understand different principles, how these drugs work. And we're going to start with the inhibitors of the cell wall biosynthesis. Few words reminding you the structure of the cell wall. Bacterial cell wall consists of what? Peptidoglycan. Based on the name, there are peptide fragments, those green bead-like things, and glycan portion, which is two different types of the saccharides, carbohydrates. NAM, stands for N-acetylmuramic acid. NAG stands for N-acetylglucosamine. NAM and NAG form long chains that are linked together by the peptide linkages. In the end, you have a lattice. Remember? That's just a reminder. We covered it all. Remember? We have a lattice. And that's what gives the cell wall rigidity. Which type of bacteria has a thicker cell wall? Gram positive. Remember, they have two layers, membrane and the thick cell wall. So if you somehow destroy the peptide linkages, leaving only this glycan chains, how will it affect the rigidity of the cell wall? It will become quote-unquote softer and the cell will pop. Does that make sense? So it will affect on a very it probably is going to have higher effect. Yes?
Why does it affect the peptides in between NAM and
Different enzyme. We'll get into that. Yes. So that's a great question actually. So what it does, how it happens, how these links are being removed. The structural element that was discovered as the component of penicillin that inhibits that enzyme responsible for synthesis of peptide links is called beta-lactam ring. Here on this structural formula, it's highlighted by like a blue color. That makes sense? You see? That's the beta-lactam ring. So this structural element of penicillin, I'm going to talk about penicillin now, but then expand it, allows it to inhibit the enzyme that is called transpeptidase enzyme that's responsible for synthesis of those linkages. Another name for that enzyme is penicillin binding protein. You follow me so far? When penicillin binds to transpeptidase, blocks its action, no linkages are made, cell wall synthesis is impaired, cell pops. That make sense? It has it's great selective toxicity because humans do not have anything like that. We don't make cell walls. Does that make sense to you? Okay. Of course, microbes quickly developed the resistance to penicillin. There were two different types of penicillins identified initially, penicillin G and penicillin V, both natural antibiotics. But when microbes developed the resistance to them, modifications were made to them. So you can see ampicillin is the form of modified penicillin G, okay? Amoxicillin is even more modified penicillin G. And finally, methicillin, completely different story. I understand you may be confused a little, saying, wait, what does that mean? Those chemicals, what do they mean? Look back at this formula in that corner. There is a letter R here. By replacing R with either of these residues, you will get the actual formula for penicillin V, penicillin G, ampicillin. Does that make sense? You see? Eventually, as you're aware, we now have a bunch of microbes that are resistant to pretty much everything. Like MRSA, methicillin-resistant Staphylococcus aureus. That is resistant to all these drugs. That was the call for developing something new. And another set of drugs that also inhibited transpeptidase was cephalosporins. It's another type of natural antibiotic that was isolated from No, I don't even have some interesting name from some fungus. Okay? So if you would look at cephalosporins, it has slightly different structure here, but it still possesses the beta-lactam ring. Of course, microbes gained resistance to cephalosporins pretty quickly. So now we are in the 5th generation of cephalosporins. So we are in the arms race. The problem is that we're always chasing microbes. They develop resistance, we have to tweak the structure of the antibiotic. And then they develop resistance. There's some data that by the time the new antimicrobial hits the market, there are already microbes resistant to it. Okay? Cephalosporins, like ceftriaxone, you probably have heard that name. They're effective, but they're not ideal. So other chemicals were identified. The class of chemicals called monobactams revealed only one member of that family, the astrionam, as the promising antibiotic. However, the final discovery came, the final relief came, when scientists discovered carbapenems. Still, all those drugs, cephalosporins, penicillins, monobactams, carbapenems, they all have the beta-lactam ring. Okay? I'm going to be going back and forth between these two slides. So this table summarizes these drugs over here. Okay? And you can see that what started as fairly narrow spectrum antibiotics, penicillins, okay, with a narrow range affecting mostly gram-positives, making perfect sense, thick cell wall, ended up with the development of the broad spectrum 3rd, 4th, and 5th generation cephalosporins and carbapenems, which have the broadest range among all antibiotics that we know. Carbapenems were like 90s. Okay? Sounds awesome. That make sense? However, of course, microbes developed resistance to antibiotics that contain beta-lactam ring. The enzyme, generally called beta-lactamase. What do you think it does? Beta-lactamase. Yeah, breaks down lactam ring. So what it does, it actually destroys this structure. Okay? If it affects specifically penicillin, it's going to be penicillinase. If it affects carbapenem, it's going to be carbapenemase. That make sense so far? So these enzymes render these antibiotics ineffective. And if you see something like beta-lactamase positive, it means that the microbe carries that gene, beta-lactamase gene, that renders a lot of those antibiotics, cephalosporins, penicillins, inactive. Now, considering that you have this enzyme, beta-lactamase, that destroys your antibiotic, how would you get around that resistance without changing anything in your drug? So again, you have an enzyme that just, No, I'm giving you conditions. So this is like a problem. You have a drug. The bug has an enzyme that destroys the drug. Can you do something without tweaking the drug? Huh? Use another drug in addition that does what? It would be too simple. Enzyme. Yes, inhibits beta-lactamase. Does that make sense? You inhibit the enzyme that destroys your drug. And in fact, a lot of penicillins are prescribed now with addition of clavulonic acid. Clavulonic acid is an inhibitor of beta-lactamase. So penicillin can still work. Guess what? Yes, there are microbes that are resistant to clavulonic acid. So they developed they evolved to have beta-lactamases that are not inhibited. So it's just a matter of time. Really, it's a matter of time. Unless you torch them, physically torch them. Okay? So, this is one way to destroy or prevent peptide linkages from forming. Can you do something else? It turns out yes. You can use the compound called vancomycin. It's a chemical produced by also some freakishly long named fungi. Vancomycin inhibits a process called transglycosylation. In simple words, it prevents formation of these chains. So new glycans are not added. That makes sense? Very effective. Good, awesome. Have you heard about VRE? Anybody who works in a hospital? VRE? Vancomycin resistant enterococcus. Huge problem. All over the world. So I mean, it's effective, but you gotta appreciate. Bacitracin is one of the most recent additions. It's the broad spectrum antibiotics sourced from Bacillus. I don't remember the species, Bacillus bacterium. It does another amazing thing. As you can imagine, to make a cell wall, you have to ship the fragments like amino acids and monosaccharides outside of the cell across the membrane, right? Bacitracin prevents that transport. So it also interferes with the cell wall synthesis, but in a completely different fashion. And it's quite effective. That makes sense? Okay, time-wise, we're going to take a break. After the break, we're going to look at the results in the lab, chat a little bit more. We have an awesome lab today.